Let me share my screen. Yes, is it visible, guys? Is it visible, guys? Is it visible? Is it
Yes,
visible,
sir.
boys? You're there?
Yes, sir.
So this is the theorem statement. This is the theorem statement. A language L is accepted by the DFA D if and only if L is accepted by an epsilon NFA E. What is this theorem all about? Listen carefully here. This is the sum that we have solved in this section. The question they asked us in epsilon NFA, and we just found out the answer. This is a sum that I have already what. It's a question, and this is the answer that we have what found out. Right. So they say that. Listen carefully here. If a language L is accepted by the DFA, if L is accepted by this DFA, right, which means that before this L should be compulsorily accepted by this epsilon NFA. Do this conversion process. So that is the idea here. So they talk about our conversion here. They talk about what? The conversion here. So that's the idea. So I believe that you have gone through the previous classes about this conversion. That's what they mean here. A language L is accepted by the DFA if and only if it will accept only if. What is the condition? If it is already accepted by this epsilon NFA. This is the conversion that we have done. So the question and the answer. They say if the answer is accepting this language, when the answer will accept the language, if my question has also accepted the language. Okay, that's the idea here. That is the what idea. We will see few examples here. Right? So listen carefully here. In our small classes, we have studied this concept of principle of mathematical induction. Right? And let me focus into this principle of mathematical induction and then come to the theorem. Principle of mathematical induction. I believe that you just remember, even if you don't remember, that few students have just texted me. Principle of mathematical induction. See, how did we prove in this principle of mathematical induction is that, see, this statement needs to be proved. This is need to be what? This need to be proved. In mathematical induction, we will take 3 steps, my dear students. Just look into it. 3 steps. What is the first step? What is the first step? The first step is that, step number 1 is, what I will do is that I will take the first case. I will take the what? First case. Here the first case is 1. I'll take the what? First step is I'll take the first case. First case is equal to 1. If I substitute n is equal to 1, I'll take 1 is equal to, I'll put 1 here. 1 into 1 plus 1. In n place I have put 1. 1 into 1 plus 1. It is 1 into 1 plus 1 is 2. So 2 by 2 is equal to 1. So LHS is equal to RHS. So the first case is proved, my dear students. So the first case is proved. So this is how we did in our small classes. So the first case is what? Proved it. So I took the first value 1, put it as LHS. Then I substituted 1 all over here. And I substituted 1. And I got the answer here. So whenever in mathematical induction, you will prove the first case. So how I am going to do it with the first case here? Please take a note of it. So this is how the principle starts here. They will say that I'll just take it and I'll just explain it. The proof statement here. The proof is given in this way. What is the proof here? So they have given this. I believe that here. So what is the proof? They say proof. We have a epsilon NFA E is equal to, it is nothing but QE, comma, sigma, comma, del E, comma, Q naught, comma, FE. What do they mean here? They mean about this epsilon NFA. Fine. They mean about this epsilon what? NFA. Be an epsilon NFA, and the DFA is obtained. So I am obtaining what, ma? I am obtaining a DFA. So what does this DFA has? Listen carefully here. D is equal to, right? Here you have to mention it as QD, comma, sigma, comma, del D, comma. Here listen carefully. Here Q naught. Here I will mention as QOD. It is nothing but Q naught of this corresponding DFA. Don't get confused. QOD is nothing but the Q naught of this corresponding what? DFA. So this is what I have found out. This is what I have found out. So this is the idea. So this is what I have done in our sum. So the statement here goes that let E be QE, comma, sigma, comma, del E, comma, Q naught, comma, FE. So this is the statement that they have given, right? So from this statement, right, so we have to prove, since all the transitions of the DFA are obtained from the transition of epsilon NFA, the language is accepted by this epsilon NFA, is also accepted by this DFA, right? My dear students, here we have to take the first case here. Here we have to take the first case here. So the first case, look at the sum here. In principle of mathematical induction, we took the first case, n is equal to 1. Here we will took this case is called as basis. Likewise, our theorem will also have a basis. Fine. Our theorem will have also a what? Basis. Our theorem will also have a what? Basis. Here, what is the first case is that W is a empty. It's a epsilon. If the string is empty, that is the first case here. Likewise, you took the first case here. Here, W is a what? Empty. So what will happen for the epsilon NFA and what will happen for the what? DFA. That's what we have to find out. Just look into it. Just look into it. I'll just make a note of it. So what will happen for the del E star of Q naught, comma, this string is empty. How I will find out? It is nothing but it is the epsilon closure of Q naught. Keep this as equation number 1. Keep this as equation number 1. Keep this as equation number 1. So what is the idea here? What is the idea here? In the first case, I will not give an input here, epsilon closure of Q naught here. I will not give an input, but still from Q naught I can go to Q1 and Q2. Right? So that is the idea here. So this is how we did. So when you do this, what output you will get? Because the output is very essential for us to figure out what is actually happening in an epsilon NFA and in a what? DFA. So for this, assume that epsilon closure of Q naught. What will be the epsilon closure of Q naught, my dear students? So you have to include Q naught. Then from Q naught you can come to Q1, and then you have to come for what? Q2. You will come forward. Q2. So this is the epsilon closure of this epsilon NFA. Fine. What do they say here is that we know that we have to find out the epsilon closure of this QOD. My dear students, just look into it. Epsilon closure of this QOD. What will be this epsilon closure of QOD? What is first QOD? QOD is nothing but, which is the start state of this DFA. What is the start state of DFA? It is nothing but Q naught, comma, Q1, comma, Q2. Remember that. Remember that. So when you find out the epsilon closure of this QOD, you have to include only this state. Only this state. You cannot include this state and other states because we don't have this epsilon transition in this what? DFA. We don't have epsilon transition in this DFA. So what you have included, inferred here is that, my dear students, listen very carefully. The epsilon closure which happened in the epsilon NFA, the epsilon closure which happened in this DFA, both are same. Both are same. Remember that. Remember that. The question and the answer. If you do the epsilon closure for this Q naught, which is the initial state, and if you do the epsilon closure for this DFA, you will get the same answer, my dear students. This is the first idea here. This is the first idea here. Remember that. So that is what. Take the first case here. Take the first case here. Here we have taken the first case n is equal to 1. Same way, I am taking the first case. The string is what? Empty. So I have to write it for the DFA also. I can write so del D star of Q naught, comma. Sorry, this is QOD, my dear students. QOD, because we are talking about a DFA. It is nothing but it is also the epsilon closure of Q naught. Both I have got the what? Same answer. Both I have got the same answer. So don't get confused here. This is what I have just shown the proof here for the sum. For the sum, this is the answer I have got. For the corresponding what? DFA I got the same. So that's what. So this is the basis. This is the basis. Look at the basis here. N is equal to 1. Right? In our small classes, again I will take you to your small class. This induction step. I'll just take you. First, what we will do is that we will find out the first case and prove LHS is equal to RHS. Second step is called as induction step, my dear students. Induction step, right? What is this induction step? This can be also called as assumption step. I'm going to assume. What I'm going to assume in this step is that I'm not going to calculate anything. I'm just going to assume that n is equal to k, and I'm going to assume that this statement is true. I'm going to assume that this statement is true. I'm just assuming this place 1 plus 2 plus 3 plus dot 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 dot. In the place of n, I will just put what? K here, and again I will put in this place k, so it will become k into k plus 1 by 2. Since my base case is true, I'm going to assume and write the same statement and say that it is true. It is what? True. So I'm going to assume now. Right? So what they are assuming in this step is that, listen carefully here, this is the assumption step. It is also known as induction step. In our book, they have given as induction hypothesis. Induction hypothesis. So what they are assuming here is that, let me write out, del W is equal to X. They are assuming W is equal to what? X. So what they are meaning here is that del E star of, I will start from Q naught and I will read the string X, right? Again, del D star, I will start from the initial state of the DFA, which is QOD, and I will read the string X. I will encounter these states. Which is QI, comma, QJ, QK. My dear student, this is assumption step, my dear students. Equation number 3. This is the assumption step, my dear students. See, what is the use of this assumption step? Here also I have an assumption step here. So what I am going to do is that when I do this induction hypothesis, from assumption step, I will take one step from the assumption step and I have to prove. Prove. In this case, next I will prove for k plus 1. What is k plus from? It is one step. From what? The assumption step. Like the same way, we will have a show that we have to prove something. So one step ahead. So then I will put W is equal to XA. So I have made an assumption and it is true. And now I am taking one step. Here I have one step is k plus 1, my dear students. Here one step is W is equal to XA. So up to X, I have assumed something. And I'm going to take one step. Right? So what is the use of this? Show that, and the assumption is that I can replace. What I can replace here is that, listen carefully here, students. 1 plus 2 plus 3 plus dot 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 k is equal to k into k plus 1. So what I am going to do here is that I can substitute this assumed value in this place. Listen very carefully. I can substitute this value in this place. So I can rewrite this equation into k into k plus 1 by 2 into k plus 1. So that is the use of this assumption step. So this place can be replaced by what? This value. Similarly, my dear students, listen very carefully here. Listen very carefully here. So I have assumed up to x. So this value can be replaced in this place. This value can be replaced in this place, and then the last value you have to find out for what? Okay, that is the idea here. That is the idea here. So you can replace the assumed value in the, you have to show out and what, find out the proof, and you have to replace the assumed value. Here I am assuming I am going to what, replace this assumed value, and the equation goes like this. They say del E, fine, del E of Q naught, sorry, Q naught comma W, this can be rewritten as del E of, first I'll write what are all the states here, because W is equal to X here. So you can write up to X, so Qi comma Qj, and you can write up to Qk, and the last values A. So they say that we have found out states Pi, sorry, P1, P2 up to Pn. Take this as equation number 4. Take this as equation number 4. Right? Take this as equation number 4. Assume that these are the states that we have what? Found out. These are the states we have found out. So they say that the next step, they say this thing. They say when del E star of Q naught comma W will be the epsilon closure of P1 comma P2 up to Pm for this is equation number 5. Fine. This is for the epsilon NFA. If you do it for the DFA, del D star of QOD comma W, if you do the epsilon closure on the DFA, both the things will be same, P1, P2. This is 6. So they say that del D star of Q naught comma W is equal to del D star of Q naught comma W. Hence the proof. So what they tell here is that, look at the sum here, students. Well, look at the sum here. If you find out the epsilon closure of Q1, right, for this epsilon NFA, it will be Q1 what? Q2. If you find out the epsilon closure of this particular state, it will be also Q1 and Q2. So if you are finding out the epsilon closure for the epsilon NFA, which is our question, which will be the same for the epsilon closure for the corresponding DFA that we have found out. So this is the idea they have put in here. So don't get confused. Don't get confused with the theorem. I'll just recap it. Basis case, they will take the first case. Here, this is our what? This is our first case. Right? This is our first case. Induction step, they will imagine something, right? And they will just assume. This is our assumption step. From the assumption step, they will put a what? Substitute here and find out. The found out thing is that, right? the string, if it is accepted by the epsilon NFA, the language will be also accepted by the DFA that we have found out, and this is the answer for that. We have to find out the epsilon closure. Both the epsilon closures are what? Same, and hence the proof. Right? I'm sorry, extremely sorry. What a blender mistake. It is del E. Del E. Sorry guys. Del E is that. Right? Hence the proof. Right? So what we have solved in the sum, it is what? Given here. I'll stop the recording and I'll just come back to you. Just hold on.